Recording. Hello. Let's have a. Would someone press one of those light switches again? So not zero, please. Okay, that's good. I also figured out that the topmost button is full lights, then it comes dimmed lights, and so on. So it's a bit weird, but never mind. Let's go to mathematics now. So having a look at these solutions. So we had some kind of estimated function, which we tend to keep on the numerics wanted to, well, typically if you have this easy estimated function, you probably can't get the real derivative, but we did this with various methods. So bisection method, second method, and then Newton's method and numerical derivative solutions. And just a reminder that now we didn't need to find the root, but instead we wanted to find some value. We did change the function so that the function is not equal to 0, but equals to 60 form, or define a new function of gx is this function minus 60. And to solution first, we find the roots of this power function minus 60. Check. In this case, under 2 rad, because we're getting this roughly 1 to 10 accuracy. And we can see right away from the iteration, from the length of the interval, we have 200 as the interval length, that when the interval does halve every iteration, we will need to take 7 iterations. So from 200 to 100, 50, 25, and so on. And we can use the center point value, so that's why the interval can be that long. So we started from 200 and 400, midpoint is 300, and got 10 that value. That was negative, so we do note in this case, our function is such that on the right side, so it's asymptotically growing function. Yeah, it's an absolutely growing function, so increasing function, monotonically increasing. So that way, the right value is the negative one, and the left value is the positive one. But you can use the same method for decreasing functions as well. Then just the negative value will be the right one, and the left side of the interval will be positive. So doable, but just need to remember that. Okay, so midpoint was negative, so we replaced the negative bound of the interval. So in this case, Yuri asked it on the previous exercise. So the formal term for the end of a full closed interval is its bound. And then calculate the new midpoint, calculate midpoint value. This is positive, so we replace the positive bound. And then fourth evaluation, and so on. And now I'm starting to skip some steps, so we're doing essentially the same way: midpoint, check value, midpoint, check value, midpoint, check value. Count how many times you need to calculate the function values, how many times you had the evaluations, and there's this value here. And then one more evaluation at this point, and we get it down to necessary length. So final evaluation is not necessary anymore, but if we calculate, we can see how far from the 0 we are. And then going back to what is 344.5 in RPMs, so times 9.5, we should get roughly 3,290. So then second method, our iteration step is this. We need 2 points. Technically, the order of points does matter, but in this case, it changes at only one step. And I did this in MATLAB, so I had this kind of a function. So I defined a function handle named power. And this tells us it's a function handle in MATLAB, so this is MATLAB syntax, and this tells that I have a variable named om. I just got lazy and didn't want to write omega. A good thing to note here, in this notation, this 5.91e minus 07 doesn't mean that it's minus 5.9 times exponential of minus 7. This means that it's minus 5.91 times 10 to the power of minus 7. So that's the kind of a scientific notation. Times omega to the power of 3, the multiplier, and so on. So this tells how much power we have. And I did already put here to minus 60. And if we have this kind of a function with power, the second method, which has now 2 variables, x1 and x2, is x1 minus power times, and this is essentially the value of the function divided by its slope. So we're having here dx, and here is the difference in power, or dy. And when we divide it, because it's now defined as a quotient, division is same as multiplication by its reciprocal. And yes, MATLAB will then evaluate power 3 times on each round, or each time I press enter after putting the second method there. So with pen and paper, you could write this down and avoid calculating the value of the function more than necessary. But well, modern computing power is relatively cheap, considering this kind of easy problems. In a really complicated problem where you maybe would need to simulate these values, then you probably would want to conserve your computing power. When I started my master's thesis, I had this one computational problem where I came to work in the morning, set up the code, went to have some coffee, checked that the code hadn't crashed, went to get a nap, went to have a long lunch, and so on. And then in the afternoon, my computer had finished calculating. So in those kind of cases, you maybe want to avoid additional function evaluations. Anyway, we start from the same points, and we know actually from this previous solution, if you did it in order, that the answer is probably closer to the 400. So that's why I picked the first x1 value as 200. So that's the one we start to ignore first, and our closer and hopefully more accurate values are then kept for slightly longer. So evaluate these values, or will I in the case of the solution sheet, I copy pasted these values from previous ones. Stopping condition is under 10 RPM. This is actually wrong here. So this should be under 1 something rad. I'll mark it for myself that this needs to be corrected. That's not correct yet. And then start after first step calculating second value, you should get this point. We can check that if we're how close we are, and we're going to need this value anyway for the function evaluation phase on the next part. And then next step should get you to 344.59. These are already pretty close. But the change here is not small enough. One more iteration, and this now changes just over 100 of a radian per second, and we get this value. So 3 iterations, 4 function evaluations, and we get our, if you evaluate the function value at x5, it's really small, so we're really close to 0. Rounding to the nearest RPM, we get 1 RPM more, but more on the same ballpark. If we selected the x1 and x2 so that x1 was 400, well, x3 is already within our accuracy, the same number, but well, x3 will be same because it doesn't matter for the formula, and x4 will be slightly different. It will be 7.1, but x5 will already be the same, and there still would stop at the same point. This doesn't always hold, so in some cases, if we pick them the other way, it might approach from a different direction, but in the case of this example, it's very smooth and does approach from the same direction as well. Okay, and then when we consider Newton's method, yeah?
Would rounding down instead of up cost avoiding this?
No. It's kind of we're already talking about accurate solutions, and in optimization, there's one important thing which I'm now going to show on the board. What the spotlighting are? Yeah, spotlighting means you're gonna see that for all. So in several cases, we do get mathematical artifacts. So if a function does have very deep values, so we have some kind of a function like this, well, even deeper. Then okay, we can, after plotting, we can clearly see that the minimum is over here. Is this visible at all for the people on the internet? It looks really dim on the screen around here. Is this a permanent marker? No, it says a whiteboard marker. So we have a wide valley here and a very deep valley, but narrow valley here. Now the problem is that if our accuracy on our device is not good enough, even if this would be theoretically the best possible solution, then if we have an inaccurate machine that gets somewhere here, when we have instead to have midpoint here, then we actually here might have a notably bad value selected. So our depends how likely do we actually end up here. So in this kind of case, using this point as the optimal value might be better because we end up being here at the bottom, which is still better than the really bad values that are over here. So that's something that you need to consider in real life, is that if you have for some machine an incredibly good optimal solution, is the machine capable of reactor or whatever, is it capable of operating on those parameters? But on some case of vibration, even 1 RPM can be meaningful. I have seen a case where they have, well, it was an EU supported project. So they used a milling machine to vibrate the tool. So usually when you see music being played on some kind of CNC machines, computer numerical controlled machines, you do probably have it tools in the air, and then the rotation speed of the servos is used for music. But in this case, they machined something so that they had the tool vibrate. So when the tool impacts the workpiece, it will start to vibrate, and they controlled the vibration so it played the Ode to Joy. Because it was an EU-funded project, so why not? So it is possible, and now we have someone asking something on chat. Yeah, it is really dim. And by the way, if you people on the internet, if you have microphones, you can also unmute yourself and talk, because figuring out that someone has sent a message on chat, especially if I'm not in front of the computer, is kind of hard to do. Or then I'd need to have someone else pick up the stream here on the classroom and tell me when someone writes on chat. But let's go on with the solutions. This was just a useful thing that we need to take into account. Okay, we have the Newton's method. This is essentially the same as the previous method, but whereas here, this part is slope or difference, this part here is actually this part here is the derivative. But because I was mean, I had you do it with the symmetrical difference quotient with a numerical derivative. You could have actually saved a few function evaluations if you would have used T's function evaluations and used, for example, just a forward derivative. But this is usually symmetrical difference quotient usually does convert faster to the real value, which of course doesn't necessarily mean that Newton's method converts faster, but I had this kind of a code for it, so I just wrote the same thing. So our function is now the power function, and then this is our symmetrical difference quotient, and Newton's method using these functions would be something like this. And I here had this hard-coded h equals 1000 part. Using these repeats, 200, and we got these values. So took 3 iterations, but we still needed 9 function evaluations. Would have needed 6 function evaluations if it was just a forward difference. We would have been probably accurate enough for our purposes. Also, starting point matters. If we had started from 400, then we would have been already closer on the first round, and then on the second round we have been there. So we would have needed, if it's roughly same values with the forward difference, we would have needed only 6 function. Wait, only 4 function evaluations. So the starting point does greatly matter when we're using Newton's method. Yeah. A note on the last example for today, or last problem for this week, rather. Now that I remember, let's grab the black marker again. Do we have white? We do. I saw Yui here with handbook. So on our textbook, by the way, this is also a note on exercises. We do have the textbook states that UdV equals UB minus integral of V du. And for some of you, what this actually means might be easier to have the same formula as it is in beta, which here states, if I write this the same way, is that G no, it wasn't that way. I might actually need to check that what way it was written there. Integration by parts. It's in the beginning of the integration section. So this is not how our textbook would state it, but actually the handbook states it like this. So fx g, this is supposed to be gx dx equals and now if I remember which way, that is the same. So f, and now we've got the integral of this minus, so f capital G minus integral of, this was capital G, right? Now I'm forgetting that, and f dash, was it that way? Yeah. And just the other way. I should have just picked it on the hand, so. Now, right. This is why I like using handbooks. I don't need to remember the formulas. Yeah, this was also other way. So. Yeah. And dx of course here. So that I'll probably want to put a note about that on the lecture material as well. So this makes it a bit more clear what we're doing in this. So we are picking some function here. Actually, the function is f, so this is written the other way. So if we take the same way as it's written there, that's why I was mixing up the capital F's and G's. So we have some function which is easy to integrate for us. And then if we can differentiate, in the case of problem 6 this week, if we can differentiate this our primary function, but we're not quite sure how to integrate it, then we can swap and use the differential tail, instead integrate some auxiliary function. But then let's have a look at inverse substitutions. And now I need to remember to share screen. And we're having week 6. No, we're already on my week 7 material. So not terribly much left anymore. The other is the old one, and this is the current material. So yesterday, sorry about that, made a bit of a mess with the lecture material. I didn't have time to have a good look at it, and the previous year's lecture material had assumed that I would have been there with the book and remembering the examples, but didn't really have them to memory. Yes, the screen share is on. I'll need to start remembering that. And okay, so this is more or less the same. And in this lecture, we're going to have a look at some of the common substitutions and inverse substitutions. So these are really common ones. So if we do this kind of a replacement, that x would be some form of sine, tangent, or secant, then we do have corresponding theta is an inverse function here. So essentially, if we see functions of this form, then we can try those replacements. An example, we are now seeing a function of this form. This reasoning for this comes that we kind of are if we would want a geometrical example, then this would be kind of comparing the sides of a right triangle. By Pythagorean theorem, we get that one, and when we do the replacement, we get cosines divided by cosines. We can take the constant out, so this square root of 5 divided by the square root of 5 to the power of 3 becomes just 1/5, and this cosine theta divided by cosine cube theta becomes cosine 1 over cosine cube theta, which is just second cubed theta. And second cube is same. Well, we can integrate that. Its integral is a tangent, and then we replace back that we get a tangent of a cosine, which happens to be that kind of a formula. Now, what we need to remember here is then that what are the relationships between various trigonometric functions? Do ask.
Didn't we talk about this yesterday?
Yes, we did. But the recording is horrible, so that's the part we're going to re-record.
Okay.
Segment of the pipe, we did also talk about that. Am I recording? That's a good question.
You were at least when you were doing the exam.
Yes, I am recording. It's good. So segment of the pipe, similar thing. So we can do the replacements, and this is already, if you remember your formulas for the unit circle, this is inspired by that. We can then easily solve that and substitute back, or solve x values and directly do from the formula. And then this we had really quickly, but now I added some detail as well. So we have polynomial, which is part of a more complex equation. We add those intermediate terms that complete the square. So we're going to have the square formula. We're going to get a squared plus ab plus b squared, or a squared minus ab plus b squared. So we get a plus b squared or a minus b squared. So we're going to look for having one of those forms. An example how we do if we have a polynomial, we can do it like this. We get these, and when we do the replacement, we get just some constant times u squared plus whatever constant is left over here into, well, okay, I didn't have marker on. So example about that, we're having a polynomial here underneath. So to complete the square, this probably is missing a square root somewhere. But yeah, we're gonna add plus minus ones there. Yes, so this should have a square root over here. So if you wonder where that pops up, I've forgotten to mark the square root. So we added plus minus 1 in the front of here, and now we can move this into this form. Let us have u is x equals 1. Well, du happens to be dx because this is just a linear function. So we get this. We know what this is. It's a derivative of the arc sine, so we can use that elementary derivative kind of and once we get that, we can then substitute u back, and that's it. So a really simple example of finding in this kind of a polynomial, we can find the square value and then get this. We can expand this to any first order polynomials, but this is in many cases, this is kind of a hybrid method. So we might also have this kind of a higher roots, which we cancel by substituting a function there, which is so in the previous we just had u equals something, which is technically a direct substitution, and now then we might remember that for the actual inverse substitutions, we take a formula and instead or take a variable and put a formula into to change the structure in a form we can solve. Now this is both, so we have a function which we replace with another type of a function. So it is kind of a hybrid substitution. Example. If you see that you need to derive something with a quotient, and a quotient has a something and a square root, and the square root has a function, you probably want to get rid of the square root somehow. So what if 2x would be u squared? Okay, we differentiate both sides, so then the derivative of 2x is 2dx, and derivative of u squared is 2u du here 10. So it's actually not a derivative, it's the result term, the multiplication. So x is the opposite here. Okay, and then so what we have in each side, we derive the function and add it to derivative dx and or du. So we get by solving dx is u du, so that goes there, and this 2x is u squared. Well, we get 1 plus the square root of u squared, which is 1 plus u on the denominator. We'll split that. Let's add 1 minus 1 to the numerator. So we can get 1 plus u divided by 1 plus u, which is 1, minus 1 over 1 plus u. Okay, this integral of 1, we can divide from the minuses. The integral of 1 is u, and then we have the part left where minus integral of 1 over 1 plus u. Okay, so what we get there, we're gonna not captionception. We have substitutions within substitutions. So substituteception, I guess. I have never seen the movie Inception, by the way, but that regardless, I've gotten to memes. So we have another substitution where v is 1 plus u, dv is du. So now we remember that when we have that kind of thing, we get natural logarithms, and we substitute those back. We got that u minus was already there on the u on a previous integral, so u minus natural logarithm of 1 plus u, and then we substitute this what x was. So if we had the x substitution of 2x is u squared, then u is the square root of 2x. Let's substitute that back. So the square root of 2x minus natural log of 1 plus square root of 2x plus c. And yeah, we might notice that the plus c might actually change value a few times. For example, here it should be minus c if we had ln v plus c, and then minus ln v minus c, but it doesn't matter here because we don't have a fixed value for that constant. It just calls for some constant to be inserted at some point of time. Another useful one if we replace x equals tangent or some other, so we could do any of these. So cosine theta is 10 toes. Let's see. So we have quotient where we have 1 on the numerator and 2 plus cosine theta on the denominator, and we want to get rid of the cosine theta. Let's substitute x equals tangent of theta over 2, and then cosine theta becomes 1 minus x squared divided by 1 plus x squared, and our d theta becomes 2 dx over 1 plus x squared. Now, at the first glance, the function looks horrible. We've got quotients of quotients. But if you look at the denominator, it does simplify quite nicely to 3 plus x squared over 1 plus x squared. Now we can eliminate the 1 plus x squared and take the 2 on before, we get just twice the integral of dx over 3 plus x squared. And this should look familiar already, because if it is of that form, we can express the integral as 1 over a tan arcus tangent of x over a. The a here is square root of 3, so that's it. Multiply by 2, so we had this 2 over there. So let's try that one. And then we substitute back to x equals tangent theta over 2, and we get that kind of formula. So now we're getting into multiple steps of doing things, but each individual step is still relatively simple. And a big issue here is that just remembering to recognize certain forms of equations. Okay, rational functions. This was something we were not really discussing yesterday anymore. So I had none of the examples and didn't completely remember what should be in the examples. So P over Q, where the degree of P must be less than degree of Q, because otherwise we would just simply simplify it and it becomes a regular polynomial. So where would you need these kind of things? These are something that we do run into with some regularity. So we want to know, for example, we are producing something that depends on a mixing ratio, and then we need to, if we know how much we produce, then we will need to, or where is the forces going. If we have 2 force components, then we might need to solve these kind of integrals. How many of you are familiar with the long division? A few, not quite all. Okay, let's have an example. 2976 over 12. So this is not sure if it's taught anymore, but this used to be primary school stuff. Now I need to rotate or just Alt tab so that I can see what I was supposed to do. Thanks. So 29. These markers are horrible. They are my own markers. Or then I'll try those markers. This is a really common ritual in our university. That is there a trash can anywhere? So okay, I'm going to throw these both markers into the trash, so that I don't then I will just move on to the next part. Okay, so now we're getting back to business. So we had 2946 over
It was 2976.
2976 over
12.
12. Okay, so of course with calculators it is more or less trivial, but how the old school way of doing this would be we write 12 here, and then we put this in Finnish we call this division angle. So tap 1 and we write 2976 here. And now we're putting 12 here. How many times we can put 12? Okay, 2 times. So 2 times 12 is 24. So we had
Should skip this time. Supposed to do 2 first, because you can't put 12 into the 2.
yeah we should do that. Yeah, we can put so the first step is can we put 12 in the 2? Yes, that's correct. We cannot. First one is at this point, so 29. We can put 12 twice, 24. So that would be here actually, and and then now I forgot completely what's in English when we add and subtract. Getting times still, and we 2 times we get 5. Now, okay, 12 is now go to 5, but then 57. So the next number we do go not quite 4 times, yeah. So 4 times is 48. We have 9 left. That's 96. Yeah, that was 4 times. And then it goes 8 times there. 8 times 12 is 96, and this was even. So now we didn't need to go decimals. So we can tell that 2976 divided by 12 is 248. So, and how many of you have done this with functions? Okay, more or less the same people. So it's also possible to do this with functions. And now I really need to remember where's my Alt tab. Okay, so now let's do it with the function of the example. So on the slide that goes on the next, so at a glance, we had this example of x cubed plus 3x squared. And we're going to divide it with x squared plus 1. Okay, so now it's going to go to x cubed x times. So we're going to have this problem from location. It's been awfully long time since I've done this by hand. And we get x cubed plus x. Because x times x squared plus 1 is that, minus of that. So we get minus x here is 3x squared minus x. X squared goes to that 3 times, and we get 3x squared, well, minus 3x squared minus 3. and then the remainder is minus x minus 3. So now we,
Or just x plus 3.
yeah, also possible. Actually, this is significant in the next step. So we get that the division of, so if we had that division of x cubed plus 3x squared over x squared plus 1, this is the same as x plus 3 minus x plus 3 over x squared plus 1. Now this is something we can deal with, and this is really easy to integrate. And let's see how the integral proceeds. And now, yep, let's put a screen share on. Okay, so we got that, and now this is why I wanted to keep the minuses there, because now with the minuses, I can remember that when I split that into smaller integrals, so we get integral of x, integral of 3, and then we get integral of minus x over x squared plus 1, and integral of minus 3 over dx over x squared plus 1. And here's the one I mentioned. Some of our examples here might skip a few. Oh, I don't get rid of those. Well, never mind. Skip a few steps. So here, this x over x squared plus 1 gets to be the natural logarithm 1, and this is some form of tangent, well, arcus tangent, so we know that from the elementary integrals. Just a slightly more complex elementary integral, but still an elementary integral. Or elementary derivative, and then looking for the antiderivative. Quite often there should be bars, but because x squared plus 1 is always positive when we talk real numbers, then that's always positive. So we got that kind of a thing done. Short division is what we could deal with also here. So we're having of the same degree. So here we had higher degree at the beginning, which we split into a lower degree function and a polynomial. And then when we have short division of the same degree, we can do it like that. So now this half here just gets a multiplier of 2 in the front. So we get the same form of the x, and then add minus 1 plus 1, and now we can split it so that we get 1 plus a constant over some formula. And again, skipping one step technically, we could substitute here to have u equals 2x minus 1, and du is 2 dx. We get the integral of this, which is the same as integral of the one on the headline, which goes to x over 2, so half x, which is the integral of 1, plus 1/4 of natural logarithm of absolute value of 2x minus 1 plus c. In many of those cases, personally, I would probably have a look if my handbook would have a formula for the general solution and use that instead. It takes some time to get used to the structure of the handbook, so Julia Test has been using it, and it's got a few hundred integration formulas, so it also makes, when you start learning, if you use a handbook, then it takes some time to learn where you find what.
Are we going to need to give all those steps in the exam?
Not necessarily, but at least state what you're doing. It's good, but not necessary. So just to be clear how to follow this, I'm giving all the intermediate steps on the lecture examples. If you have a look at the textbook, this is Adam's example 6 or something on there, then it does actually skip the intermediate steps. But for especially those of you who haven't done this by hand in a while, it makes it a bit easier to follow when there are the intermediate steps, and it isn't just quicker thing. So on the last exercises, I was talking about proofs. So there is a joke that the greatest operator is the VMA operator. We may assume, and then something follows. But that's perhaps not a good teaching material, which has some other formula which just say that this is obviously the same as the following, and then a complete logical jump into a formula of a different shape. So very common ones are that if you see 1 over ax plus b, it is of the form of 1 over a, natural logarithm of ax plus b. If you see x over x squared and so on, you get this another one, x over x squared minus a, another shape, and so on. And then this 1 over x squared plus a squared, or a squared plus x squared, it doesn't matter. Then you get those tangents. The difference between the second and the third is that there's a 1 on the numerator, not x. And with the minus, we still go to natural logarithms. And yeah, that's it for today. Any questions? I'm gonna stop sharing so nothing on the chat. All right, so next week our final new piece of theory before the exam. I'll try to get the exam done. I should get you also the exam formula sheet so you can familiarize yourself with it, and then we start. Well, I think there are a few more exercises left, and then the exam. Yeah, to ask.
Is the exam week on the 19th of October?
Yes. Oh, it is important. Yes. Let's actually share your screen for a moment. And I wanted this one. So where do you find exam information? Is can I get this away? No, apparently not. Well, uni.lud.fi. For me, this comes in Finnish, but let's move it into English. Studies, under panel studies, you have examinations. I guess it is probably in SISU somewhere as well, but in daily scheduling, find engineering math, interim mathematics 1. This dash B is the midterm. It's on 23rd of October. It's a Friday, and the exam will be at 4 o'clock. Not the best possible time, but well, better than Monday, 8 o'clock. So I haven't checked when the main exam is. So let's grab the course code and start looking, because last year our main exam was 8 o'clock on the 2nd of January, which was more like, oh. So our final, this kind of second, well, the end terms are on the 17th of December, also 4 o'clock exam. And technically there should be a final exam on the 8th, but if you have everything we go through into this half a year, in one big exam, that's maybe not an exam I'd want to take. So those of you from Finland know ylioppilaskokeet, so tend to be roughly of the similar preparation as those. So
And that's in 3 hours.
in 3 hours, yes.
Yay.
So preferably take the midterms and end terms.
We just applied for the exam.
Yeah, it's on CISO probably. It used to be in Audi, and do note that you usually need to register to the exams at least, does it say, practical instructions, normally 3 hours unless otherwise mentioned, arrange on those times. Examination rooms will be published in the morning of the examination day, so there should be those information boards that tell which exam is in which room. On time, no mobile phones, leave all other items in the bag, including wristwatches, and you're allowed to keep handbooks, calculators of any number, of any kind. Well, what you can tell the vigilators that it's a calculator, honest.
Just roll off the suitcase of calculators.
And no talking, and no being late more than 15 minutes. You're not after that you're not allowed to enter anymore.
Be early
You can be early.
in the room or
Usually there will be some arrangement made, like they're gonna lay the papers on the table. So probably they're gonna tell you that there's, not sure now, but in the old times, the papers would be color coded, and then they would be telling that people who are attending the engineering maths exam, you have the red papers. People who are attending the electrical engineering exam, you have the green papers, and so on. You have to be there at least 15 minutes, and after that you can leave. But it probably takes slightly longer to actually complete the exam. Student card can be used. Oh, no, sorry, mobile version of the student card cannot be used. So you need to bring IDs. And where was the registration information now? Yeah, important, registration for the examinations. So you need to register a week before the examination.
and registering in this case.
It takes place in CISO. So you tick that, yes, I'd like to attend that one.
By ID, would that mean like an actual
Student
ID
card,
or
preferably.
Preferably student card.
Student cards.
What if I don't have a physical student card? Is an ID
Bring an ID 10. So it said the mobile version of the student card cannot be used, and bags cannot be fetched until the answering papers have been left. Yeah, present identification, e.g. passport or driving license or anything that has your picture on it.
I mean, actually, driver's license isn't considered.
Yeah, it's not. If you go to banks, driver's license is not a formal identification. Back in the day, I used to present my student card. I have actually lost it because I could use my student card still as a library card in the university library for until very recently. So I do have a very young picture of me in the student card. Yeah, if you have any question on the exam, do ask, and you need to register 23 minus 7. So it's on the 16th, yeah, 16th the latest. You can register early.
I registered for over 1.5 months.
Yeah.
So if you're taking the
All right, so that's it. I'm gonna pause the recording.